The Eastern Sierra is a land where snow-capped peaks contrast starkly with high desert basins and ranges. It is also home to dormant volcanoes, ancient lava flows, and geothermal hot springs and geysers, dramatic reminders of the Eastern Sierra's dynamic geology. Conservationist John Muir described it as frost and fire working together in the making of beauty. In this program, we'll explore volcanoes by putting you right in the middle of one. As you travel north on Highway 395 out of Bishop, the granite peaks of the Sierra Nevada mountains seem to dominate the landscape. But did you know that once you cross Sherwin's summit, a 7,000-foot high mountain pass, you're driving into the heart of a prehistoric supervolcano? The volcanic eruption that took place here was an explosion that dwarfed the one on Mount St. Helens in Washington by more than 2,000 times in power and size, leaving behind a 200-square-mile crater called a caldera. Dina Vineski, a geologist for the U.S. Geological Survey, describes how the Long Valley caldera was created.
The caldera itself formed 760,000 years ago, and basically there was a source of magma under the surface. And when that magma erupted, there was nothing to hold the ground up. So the ground fell, and it formed this oval-shaped depression in the ground, and that's the caldera.
Supervolcanoes are so massive that they can affect the climate, plant, and animal life of the planet. When the Long Valley supervolcano erupted, it belched out tons of superheated ash, gas, and rock several miles into the sky. But what goes up must come down, right? Much of the ash thrown out of the caldera returned to partially fill the massive oval-shaped crater. Thousands of additional cubic feet of material settled within a few dozen miles, creating the rugged volcanic tablelands that surround the blast zone. A good place to see an example of this is to the southeast of Crowley Lake. Those salmon-colored bluffs, known as the Bishop Tuff, are cooled deposits of silica-rich ash, lightweight pumice, and other volcanic debris. But as Dave Wagner, a retired geologist from the California State Geological Survey, explains, not all of the ash stayed close to home.
The distribution of the ash and the direction of the flows are partially directional depending on how they erupted, but once they're in the atmosphere, it pretty much depends on which way the wind's blowing. There was ash that traveled as far east as Kansas, as far north as Wyoming, covered nearly all of Arizona and New Mexico, and did cover all of Utah, Colorado, and all the way to the Pacific coast and into the ocean itself.
Volcano comes from the Latin word Vulcan, but it has little to do with the sci-fi cast of Star Trek. Vulcan was the ancient Roman god of fire. And although the Long Valley eruption and collapse took place hundreds of thousands of years ago, a reservoir of hot magma still lies below the caldera and continues to bubble with life as it heats the underground water feeding local hot springs. Near the Mammoth Lakes exit off Highway 395, rising steam marks the place where over a century ago, weary travelers marveled at the Casa Diablo geysers. Earlier still, the area was a bustling stagecoach stop. And before that, a sacred gathering place for native Paiute tribe members. Today, a modern geothermal plant harnesses the hot springs and converts the Earth's natural heat into clean, renewable electricity. But arguably, the largest tourist attraction in the area is Mammoth Mountain, the highest point on the rim of the caldera and one of the West's premier ski areas. But as Dr. David Hill, chief scientist in charge of the USGS Long Valley Observatory, points out, it also happens to be a volcano.
Mammoth Mountain erupted between 100,000 years and 50,000 years ago. It's along the same structural chain that runs all the way up to Mono Lake. And that chain, the Inyo Mono volcanic chain, is a chain that's erupted 20 times in the last 5,000 years.
The Long Valley caldera is so enormous, it's hard to see from one spot, but the top of Mammoth Mountain offers an excellent view. USGS geologist Dina Vaneski hopes you'll make time to explore it for yourself.
It's really exciting to be able to ski or mountain bike on a volcano. If you take the chairlifts up to the top, you get amazing views of the Long Valley area, and you can see some of the volcanoes and some of the craters and some of the domes.
Mammoth Mountain, however, is by no means extinct. Like many of the volcanoes in this chain, which are considered to be dormant or sleeping, they will occasionally stir with life. And that's what makes this one of the most interesting and intensively studied volcanic areas in the world. In the last 30 years, monitoring by the United States Geological Service has revealed recurring swarms of small earthquakes beneath the region. Steam vents occasionally give off the distinct sulfur smell of rotten eggs. And hot springs, like the ones at Hot Creek just northeast of Mammoth Airport, frequently change temperature from pleasant to boiling when fractures in the volcanic rock release superheated water without warning. Fortunately, volcanic activity usually doesn't come unannounced. Dr. David Hill has kept track of seismic rumblings in the Eastern Sierra for 4 decades and leads a team of USGS scientists who have their finger on the region's pulse. Similar to a patient in an emergency room, the area is continuously monitored with special instruments like seismometers and GPS satellites to detect any earthquakes that signal the movement of magma beneath the ground. A system of coded alerts is also in place, each with a specific plan to quickly notify people if conditions grow dangerous. So, should visitors be concerned of another super eruption?
There's really no evidence that there's a large volume of magma in the crust at the present time that would be capable of producing such an eruption. We're much more concerned about smaller eruptions, and as with most things in nature, small things are much more frequent than big ones. It's true for volcanic eruptions. It's kind of the legacy of the West. We live in this beautiful area. It's beautiful because of these active geologic processes, but they come with a hazard, and we need to know what that hazard is, understand and be prepared to deal with it if that hazard should develop.
To learn more, we invite you to stop at one of the visitor centers along Highway 395. Ride the seasonal gondola up Mammoth Mountain to explore the Top of the Sierra Interpretive Center. Or check out the Roadside Heritage or USGS websites.
The mining history of the Eastern Sierra is as varied and spectacular as its extraordinary mountains. From the native Paiute people's mining of obsidian for tools, to prospectors in their quest for gold, to the modern-day excavation of pumice for industrial use, the mineral wealth of the Eastern Sierra has been explored and unearthed for centuries. It was the glint of gold that first caught the eye of John Marshall in the Sierra foothills in 1848. 1 year later, an epic immigration brought adventurers from around the world to the California territory with hopes of staking their claim. But it wasn't long before wealthy businessmen seized the most lucrative opportunities, and the lone prospector's dream of striking it rich in the western motherlode country had all but died. It was a hard job finding ore profitable enough to be mined, especially when a prospector had little more than a pickaxe and shovel to help. The task required lots of manual labor. And as professor of mining engineering at the University of Nevada, Reno, Dan Taylor points out, a little bit of curiosity too.
Basically, what people knew then in terms of exploration is they would look for surface expressions of the mineral they're after, such as flakes of gold in the sediments in a creek, and then they say, well, where's it coming from? And they found that it was coming from an outcrop, and they started mining down the outcrop and building underground mines from that.
When word got out about the discovery of new mineral deposits on the other side of the Sierra crest, echoes of another gold rush reverberated, this time from west to east. In 1857, a gritty young prospector named Cord Norst lived with his wife in a hut made of stone, aspen, and willow at a spot that today is a turnout at the base of Conway Summit south of Bridgeport. It came to be known as Dogtown, reflecting its primitive living conditions. Norse panned considerable gold from the adjacent creek, and an onslaught of prospectors soon followed. 2 years later, the discovery of silver in the Comstock lode near Virginia City, 100 miles north, transformed the rush to a frenzy. Over the next 2 decades, mining camps, villages, and towns seemed to spring up overnight in places like Cerro Gordo, Mammoth City, Lundy, and Bodie. By 1879, gold had turned the remote mining camp of Bodie into a full-fledged boomtown with a population of 10,000 people, 2 churches, and 65 saloons. In its time, Bodie mines produced $34 million worth of the precious metal. But by the 1940s, the place was a ghost town. Today, some 150 abandoned buildings are preserved at Bodie State Park, where seasonal access is available off Highway 395 just south of Bridgeport at Route 270. So why was the region blessed with all this mineral wealth? It turns out that the earthquakes and volcanoes involved in the process of mountain building in the eastern Sierra millions of years ago were also responsible for something else. Tommy Thompson, professor of economic geology at the University of Nevada, Reno, talks about another geologic contribution.
Certainly in the western U.S. and the 395 corridor has a lot of geothermal activity, and it's those areas where hot waters have been moving that typically also have mineral deposits that have formed or are forming at the present time.
Residual fluids from cooling magma miles below the Earth's surface force their way through cracks and fissures in the bedrock of the Sierra Nevada. These solutions are rich in minerals and precious metals, and as they rise and cool, the minerals are deposited, often in the form of veins. Silica, one of the last minerals to be deposited from these fluids, forms quartz veins. Gold, which does not react with any other elements, is often found in quartz veins as the last of these fluids crystallizes. This is why miners look for gold where these quartz veins occur. Major advances in the study of ore bodies followed the discovery and development of the metal-bearing veins in the western United States. Today, geochemical detective work suggests much of the gold taken from the western mother lode actually came from central Nevada, which was once a high plateau with ancient rivers that deposited the nuggets down the slope of an ancestral Sierra. But Old West history buffs and the U.S. military aren't the only ones interested in the mines of the eastern Sierra. As Tommy Thompson suggests, geologists believe that many of these original mines are far from tapped out.
We found most of those things that are exposed to the surface, and we need to start looking in areas that require a remote sensing technique, looking at trace element chemistry, geophysics, the rock alteration effects, and hopefully recognize something that's well above something that is found at depth.
The legacy of the mining industry, however, has been problematic because for more than a century, very little thought was given to the environmental consequences of what was left behind after all the digging was done. Taylor reflects on the past and the future.
We've come a very long way from Bodie when people were either swinging a pick at the rock or using a 4-pound hammer and a short piece of steel to drill holes and packed it with black powder and blew it up and tunneled into the ground. We're trying to figure out how to clean up the messes that other people left. A lot of research on how do we make sure that nothing is escaping from our current mining operation is being used on how to clean up the abandoned mines. So there's a lot of synergy in the science and in the engineering to deal with problems like that.
Mining forever changed the eastern Sierra and tamed one of the last frontiers of the American West. By following the example set by the native Paiute people, it is our commitment to be stewards of the land. And as prospectors in a new century, science can help us understand where these resources are and how they can be developed in responsible and innovative ways.
Scattered in the sage and sand along historic Highway 395 are chips of obsidian, volcanic glass left behind by the Paiute people, some of the early inhabitants of Owens Valley. Obsidian is typically born from thick, oozing, silica-rich lava that quickly cools with the last pulse of a volcanic eruption. Native Americans prized obsidian because a skilled person could craft this hardened glass-like lava into valuable tools and arrowheads. Calderas and volcanic domes throughout the Eastern Sierra provided numerous sources for this glassy black treasure. But you couldn't just work with any rock. Obsidian flecked with white was less desirable because that meant it had mixed with pumice and ash when it cooled, making it weaker and more brittle. High school teacher Gerald Howard was born and raised in Bishop, and his ancestry is a mix of Miwok, Paiute, and Shoshone. Howard confirms that when it came to picking stones, experience was the best teacher.
Like anything else, if you've done it for a while, you'd know exactly what you're looking for, what the best material is. One of the unique things about the Owens Valley is that the obsidian is pure, pretty clean. It doesn't have too many imperfections.
Tom Mills, an archaeologist for the California Department of Transportation who has studied Owens Valley prehistory for the last decade, describes obsidian's versatility.
It was incredible. It sharpened wood, sharpened branches, scrape hide, cut meat, right through tendons, cut right through bone. It was the Leatherman tool of prehistoric times. It really was. It could do anything.
Retired science teacher and Owens Valley native Dennis Brackett offers an explanation for this rock's amazing properties as a cutting tool.
One unique thing about obsidian is that it breaks in a very predictable fashion. Geologists call that conchoidal fracture, which means shell-like. You can see on a flake that's been struck off of a piece of obsidian that it does sort of resemble the back of a seashell. It has a curving pattern, and of course, this struck flake is really quite sharp.
A well-crafted obsidian blade has a cutting edge many times sharper than a steel surgeon's scalpel, which is why, in recent times, some doctors have used them during eye and heart surgery. Native American tribes like the Paiute have always appreciated the superiority of this typically black, glassy stone and utilized it for much of their toolmaking throughout the Owens Valley. Gerald Howard has seen firsthand some of the remnants of all that hard work.
I went to get wood up by the Glass Mountain, and I was going there late in the afternoon. The sun just hit right on the road, and you could just see it was sparkling because of all of the chips on the road.
Obsidian was definitely an item of value, a commodity that was sometimes exchanged or traded over distances of hundreds of miles. Along with pine nuts from local desert mountains and salt from the shores of Owens Lake, obsidian was the currency of choice for the Paiute people and was traded across the mountains as far as Nebraska. Paiute elder Gerald Cyn recalls stories his father and grandfather told him about old Paiute trade routes through the Eastern Sierra and their importance to his people.
Wherever you go, our people have been there. The passes over the mountains were used frequently in the spring and summertime when they would travel to trade, and our people would take things with them that they could trade because that was part of the learning process.
Archaeologists are learning too, and like detectives, always searching for clues to help them piece together a picture of the past. Because animal or plant material decomposes over time, stone tools are often all that is left to tell the story of an ancient people and their travels. But simply studying the shapes and styles of prehistoric obsidian tools discovered in the field provided limited evidence for reconstructing the picture of a changing culture. To do that, they needed to know more about the obsidian itself. But the rocks couldn't talk. Or could they? As Craig Skinner, director of the Northwest Research Obsidian Studies Laboratory, explains, a powerful new tool opened the door for archaeologists, giving them a way to look into the rocks and into the past.
One of the unique attributes of obsidian glass is that almost every obsidian source is chemically unique. In the 1960s and early 1970s, it became possible because of advances in X-ray fluorescent spectrometry to non-destructively analyze artifacts for multiple trace elements at the same time.
This new technology allowed scientists to investigate even the smallest artifacts.
Most of the material that we see and analyze in the lab are tools, that is, projectile points or biphases. But a great deal of the material is just debitage or chipping waste that results from the modification of the stone while it's being manufactured. But using only this, we can actually reconstruct quite a lot about the nature of the site, both the sources of the artifacts and chipping material and the age.
This geochemical technology uses X-rays to bombard the obsidian and reveal its composition. Just as every person can be identified by a unique fingerprint, every obsidian outcrop and every handcrafted obsidian tool has its own fingerprint.
Using a variety of different trace elements like rubidium, strontium, zirconium, niobium, barium, we can essentially fingerprint individual obsidian sources. And we can quantitatively determine in parts per million how much of each of these trace elements is present. Then we look for matches based on the patterns of these various trace elements and their different abundances, and we can generally tell what geologic source this particular artifact originated from.
Now obsidian has much more to say to archaeologists about the ways of ancient people and the places they've been.
So when they find obsidian and arrowheads on the other side of the mountains on Nevada into Idaho and Colorado or wherever, they've found out that the obsidian comes from the Owens Valley and makes the story that our people told down through the ages true. Otherwise, those things wouldn't be there.
To learn more about obsidian and the Paiute culture, stop by the Eastern California Museum, just off Highway 395 in Independence. Watch for signs.
Spectacular vistas and unspoiled wilderness abound in the Eastern Sierra. However, Dr. Yelmer Irkins, a professor of archaeology at University of California, Davis, sees more than the stunning scenery. For despite the extremes presented by the region's climate and landscape, this is a place where humans have lived and thrived for thousands of years.
We know from the archaeological record that people were living everywhere. So as you drive along 395, you can just picture that there were little villages dotting the valley floor. You can't walk 100 meters across most of this area without walking across archaeological sites where people in the past were living.
Reminders of these past cultures range from obsidian chips thousands of years old left by the first people in the Owens Valley, to historic artifacts like stone fences and rusted ore buckets from the many who came after them. Preserving this legacy is the goal of archaeology. In their studies, archaeologists sift through the dirt, seeking to construct a chronology of the past, reconstructing ways of life, and hoping to understand why human culture has changed through time. Greg Haverstock, an archaeologist for the Bureau of Land Management, compares his work to that of a painstaking detective.
We're trying to uncover a mystery. There may not be a crime there, but human activity took place there and they've left evidence. And unfortunately, it may be 10,000 years have passed, so it's an extremely difficult job. And we're often looking at people's trash or the remains of their activity, so there's a little bit of deciphering that goes on in that regard. And if we're intelligent and use a scientific method, we should be able to gather data and make conclusions that we can support and determine what happened before.
Manzanar National Historic Site Ranger Interpreter Nancy Hadlock reminds us that in spite of what we see in popular movies, archaeology is about more than searching for ancient treasures or Egyptian mummies.
Archaeology covers all times of history. We find shotgun shells and bullets and things like that. It's not a science about just dead people. It is a very, very modern, active science that covers lots of different time periods, all of which are really fascinating.
Artifacts, or human-made objects, tell us about a people's technology, their lifestyle, and even their trading relationships. But because of the extreme climate conditions in the Eastern Sierra, it is mostly stone tools that are left here to tell the tale.
We live in a pretty dry environment, but we don't have a whole lot of archaeological sites that are in big caves. And that's really where you find good preservation of perishable products. So it's very rare for us to find neat things like baskets or rope and twine.
What archaeologists do find in abundance in this region are obsidian chippings and projectile points, which is one reason they're the focus of extensive research and analysis in constructing the chronology of past lives. But Dr. Yelmer Irkins encourages others in the field to remember that artifacts offer only one side of the story.
Working with Native Americans has been good for archaeologists. It gives us a very different perspective on prehistory. A lot of archaeology is anthropology, and so we're trying to understand broad general patterns in human history and human prehistory. For people at Owens Valley Paiute, they're interested in the specific what happened here in this location with my ancestors.
To understand how Native American tribes, like the Paiute, made a living in these kinds of arid environments, Dr. Eerkens reveals there are places in this landscape yet to be explored by an archaeologist's trowel or shovel.
In some areas of Owens Valley, about 600 years ago, we don't know exactly when people began irrigating, digging irrigation canals and flooding areas of the valley bottom to promote the growth of different kinds of natural resources. They were actively modifying and taking care of the environment.
Richard Stewart, a member of the Big Pine Paiute tribe, grew up in the Owens Valley, learning cultural traditions from his grandparents.
A lot of the Indians in Big Pine and in Bishop, they had their irrigation system set up. They were irrigating native plants like taboose, which is a nut grass.
So they realized that by flooding the areas where the taboose grew, that it would produce more nut. So when they got the snow melt, they would divert the creeks and flood those areas.
They knew how to construct their ditches so they didn't wash out. When the ranchers and everything came in, they simply took the old Indian ditches and expanded them and made them more usable.
50 miles south of Bishop, just west of Highway 395, travelers will find an archaeological site where evidence of multiple periods of human settlement are being documented. Longtime National Park Service ranger interpreter Nancy Hadlock talks about the current research at Manzanar National Historic Site.
Well, Manzanar is kind of a unique location because it actually has different layers of history, different layers of archaeology. So we are doing a lot of research into the Paiutes that were in this area. We do find artifacts from that time period. We also have a period of time when this was an orchard community. And then most recently, of course, was the Japanese American internment camp.
Following the attack on Pearl Harbor in 1941, Manzanar became one of 10 military-style camps where Japanese American citizens were held during World War II until 1945. Over the years, spring runoff from the Sierra Nevada snowpack periodically flooded the abandoned site, burying the camp with silt and sand. Now a National Historic Site, NPS archaeologists at Manzanar are working to excavate and stabilize this one-time home for thousands of Japanese families.
And that's really archaeology. I mean, it isn't just digging the things up and discovering things. It's what they tell you. These things tell us about the people. They tell us stories.
Which is why Dr. Yelmer Eerkens reminds us that if we want those stories to continue to be told, we must understand that in archaeology, context is everything.
All of the archaeological resources are, of course, protected by federal law, and it's great to go out and look at these things, but when people pick up and take those artifacts away, they're removing our ability, our collective ability as archaeologists and as Native Americans and as the general public to understand how people were living on this landscape in the past.
When we take time to read the signs and unearth those relics and treasures, it gives us tangible proof of the creative and inventive ways humans have been able to adjust to and live in this extreme environment. If you'd like a closer look at some of these artifacts and their stories during your travels along Highway 395, you can visit the Eastern California Museum in Independence, Laws Railroad Museum in Bishop, Manzanar National Historic Site, and the Mono County Museum in Bridgeport.
Every road sings a tune. Route 66 is classic rock and roll. Highway 1 is a dreamy New Age ballad, while US 395 is a fiddler's ode to the West that seems to evoke cowboy boots and roadside diners. Nicknamed the Mother Road of California, Highway 395 was once called the Three Flags Highway, as it ran for almost 1,500 miles from San Diego through Nevada, Oregon, and Washington State. Today, although 200 miles shorter, Highway 395 is still the main route through Inyo and Mono counties, where miles of 4-lane expansions now make for an easy drive. In the early 1900s, though, the trip from Los Angeles to the Owens Valley would take 3 days on dirt roads. Brad Medham, Deputy District Director of Planning and Programming with District 9 of Caltrans, the California Department of Transportation, understands the challenges of building roads in such a unique environment.
Since 1955, we've been working on developing a corridor to allow people to get up and down through the Eastern Sierra. And the environment is unique. In our district, we have the highest and lowest spots in the California State Highway System. So Tioga Pass is at 9946, and out by Badwater we have a stretch of highway that's at 242 feet below sea level.
Over the decades, road building has become a sophisticated, technology-based endeavor. Surveyors now use global satellite positioning to determine road grades. And since driving in the Eastern Sierra is hardly a straightforward proposition, mountain curves are being re-examined for engineering safety.
We have a little tool called a ball bearing curve. And basically it's like a protractor turned upside down, but it holds a ball bearing. And as you drive around curves at different speeds, that ball bearing will swing to the side. So we know exactly, how much centrifugal force is being put on the vehicle. But all of that was done with like a, 1957 Chevy. Well, now of course we all have nice cars with great suspension, and so we all take those curves faster than the sign. So that's the dilemma that we're facing with that.
So if the cars have changed, why haven't the speed signs along the curves? To replace every one involves not only time, manpower, and money, but raises the question of how to warn drivers that the new speeds wouldn't be a license to treat mountain roads like the Le Mans Grand Prix. Maintenance issues like sign replacement or road repair are generally summertime jobs. The winter months bring a different set of concerns for travelers and road crews on Highway 395. From Bishop to the Nevada state border, the highway crosses 4 significant mountain passes at elevations up to 8,000 feet. Here, winter travel can require snow chains, 4-wheel drive, and lots of patience, especially when high winds, whiteouts, and even avalanches can close the road at a moment's notice. Sue Burak is a hydrologist and avalanche forecaster for the Eastern Sierra Avalanche Center. It's a job that has little room for error, since the end result can be a matter of life and death.
The Sierra is known for its relatively stable snowpack, which it is 99% of the time compared to other snow climates. But when it's not safe, when it's unstable, it's really unstable, and that's when people get caught and hurt.
So what causes an avalanche in the first place?
Simply put, the snow falls from a storm and it gradually builds up layers. And if there's no disturbance to the snow on the flat ground, it'll remain in place. When you have snow falling on an inclined slope, one of the forces acting on it is gravity. And if you have enough snow fall that adds enough mass in the form of the water that's contained in the snow, then that slab will fail and detach from the slope.
During the winter, don't look for Mike Weir behind his desk. As Mountain Area Superintendent for Caltrans District 9, you'll find him out in the field analyzing snowpack conditions to keep the highway safe for travelers in the Eastern Sierra.
The mountains will talk to you. They'll let you know what's happening up there. And we have what we call indicator slopes. We will dig our snow pits. And if those things start moving, we get a lot of snowballs, or we can see a little cracking or slipping and stuff, then we do our avalanche control work.
That work used to mean firing rocket-like projectiles from a small cannon into the snow-covered mountainsides. However, Homeland Security's concern about the misuse of these firearms prompted the development of new technology.
So we have what they call a gas-X system. It's a great big tube, looks like a candy cane sticking out of the mountain, and it's all controlled by a computer that we can take in our pickup. But it fills up this holding tank with propane and oxygen, and then you hit that little spark plug igniter, and a big ball of fire comes out and explodes over the snowpack and causes an avalanche.
Department of Fish and Game wildlife biologist Tim Taylor reminds us that winter isn't the only season to challenge motorists along this highway.
People need to know that when they're driving up 395, anytime from about early April through sometimes late October, mid-November, they're in jeopardy of hitting a deer.
In the Eastern Sierra, fishing, camping, and hunting seasons all coincide with the migration of several mule deer herds, foraging at lower elevations when it snows, or traveling to higher elevations during summer fawning season. Unfortunately, Highway 395 creates an intersection of trouble across these long-time migration corridors. In the mountainous terrain just north of Bridgeport, huge yellow signs with flashing lights warn drivers that this stretch of road is a major deer crossing. Yet despite these highly visible cautions, Caltrans has counted an average of 18 deer fatalities each year in this area since 1965. These numbers have caused concern for the safety of the deer, local residents, and travelers alike. But is there a solution?
What's been shown in the literature to be the only thing that really works is getting them off the highways.
Taylor, who is responsible for wildlife resources in Mono County, isn't talking about taking the cars off the road, just the animals. That's why state and federal agencies will soon be installing 2 wildlife undercrossings in this area. And as Taylor points out, deer won't be the only ones to benefit from them.
We have a large black bear population. They need to disperse, especially juveniles. They're crossing the highway all the time, and they're hard to see at night, and they get hit as well. So there's lots of species that we're concerned about other than just mule deer.
It's a priority for Brad Medham of Caltrans to keep travelers, wildlife, and work crews safe along the Eastern Sierra Scenic Byway.
To slow down when there's construction going on, because we've got people out there working, and we don't want to lose any of them.
And Mike Weir asks you to consider this before your next trip.
Caltrans and the CHP would rather people get to their destination, without being in a wreck. Snow won't melt before you get there. Slow down so that when you get to your destination, you can enjoy it.
As you travel Highway 395 and experience the stunning scenery of one of the world's most spectacular outdoor playgrounds, listen for the melody of that fiddler's tune, or compose a song of your own and let this historic highway take you back to a simpler time.
Playing across the jagged spine of the Sierra in a howling fury or a whispering caress, mountain weather can be a symphony of winds, especially as you climb high into the passes of the Eastern Sierra. On a hike up to Bloody Pass near Mono Lake in 1902, avid birdwatcher Walter K. Fisher stopped to observe some Clark's nutcrackers and commented in his journal, "All the Clark crows appear to go through this pass in great haste. When they attempted to fly westward against the wind, I noticed one lazy fellow who gave up in disgust and turned tail, all his feathers trying to outstrip him in the race." The Sierra winds that defeated those birds made a world champion out of hang glider pilot Carrie Castle.
It's known for some of the biggest air you can ever experience in flying. Kind of like, how surfers go to Hawaii for the biggest waves. Well, people come to the Owens Valley for the biggest air. Air currents, big, strong thermals going up and going up high.
Much like the tides in the ocean, wind can be thought of as tides of the sky. But these tides of air movement are invisible unless there are clouds. The Eastern Sierra weather story is written in the wind and clouds. Dr. Laura Edwards, a meteorologist with the Desert Research Institute in Nevada, tells us that regional weather data has been collected for over 100 years, giving us a long and continuous record of weather patterns.
Climate's important for giving us a baseline for forecasting. So there's a lot of different components that go into forecasting. Watching climate change, and also just knowing the local complexities. It's very hard to really pinpoint what's happening in the Eastern Sierra because it's such a narrow space, the incline, the steepness of the mountains. That's why it's so difficult to forecast.
Daily weather and climate variations are determined by topography and geography. Many contend that the Sierra Nevada has the steepest orographics, or weather that's related to terrain, in the United States. It's not hard to see why. The huge granite wall of the Sierra Nevada range sits directly in the path of the moist westerly winds that blow off the Pacific Ocean less than 90 miles away. Large bodies of water tend to moderate weather patterns, so the Sierra Nevada range experiences more moderate temperatures than regions farther inland. The Eastern Sierra climate might best be described as pleasant, featuring hot, dry summers and relatively mild, wet winters. Such a combination is considered rare among the mountain ranges of the world. A high-pressure air mass, known as the Pacific High, sits over California from late spring to early autumn, deflecting storms and causing most days to be drenched in sunlight. In the late fall, it moves south, opening the door for winter storms. When storm clouds move in from the west, they must cross the towering Sierra crest. As they rise up, most of their rain or snow falls on the range's western slopes. By the time the clouds reach the east side, most of their moisture is gone. This so-called rain shadow effect keeps the eastern slopes much drier and influences the type of plants that grow in this high desert climate. Another unique occurrence takes place when fierce storm winds blowing 50 to 100 miles per hour bring a cloud, recognized as one of the signature landmarks of eastern Sierra weather, the Sierra Wave. This mountain lee wave, a current of air that rises and drops, often generates huge flying saucer-shaped clouds. These lenticular clouds form pancake-like stacks at altitudes of 30 to 40,000 feet. They seem to hover in the sky as the flow of moist air continually forms the cloud from the windward side, while it evaporates on the drier leeward side. Although such clouds are seen in other mountainous places like the Alps and Andes, the cloud formed by the Sierra Wave can dominate the sky and has been known to run the length of the Sierra crest for over 200 miles. Ron Smith, a meteorologist from Bishop, California, describes how a Sierra Wave is formed.
You've probably seen when you have a large rock in a stream that downstream from the rock, the water takes on an undulating wave pattern. And the waves are standing waves. In other words, the peak of a wave will stay stationary. New water comes in and water flows out of it, but the location of the wave remains stationary. Well, air is really just a thin liquid. So as that westerly flow of air moves across the Sierras, we get these standing waves. And as the air moves up, it cools and condenses, and at the top of that wave, you get a little cloud. And since the wave is rounded at the top, it looks like a flying saucer.
In the 1950s, meteorologist Hal Cleforth participated in the Sierra Wave Project based in Bishop, California. This intense atmospheric research effort was aimed at exploring the cause and dynamics of these clouds. While on reconnaissance for this project, he and Larry Edgar set a still unbroken world glider soaring record, riding the updrafts of a Sierra Wave to 44,255 feet. A current extension of the Sierra Wave project is the National Science Foundation-funded Terrain-Induced Rotor Experiment, also known as T-REX. By studying the turbulent rotor clouds found in the Owens Valley, researchers hope to explain the phenomenon of these intense circular moving air currents and its significance for forecasting mountain weather. Hal Cleforth comments on the importance of this study.
The major problem for aircraft in the Sierra Wave is a pilot flying from the east, trying to cross the Sierra, facing into a wind of 50 to 100 knots, which slows him down, and then facing a downdraft of 2,000 feet a minute, so that in 2 minutes he can go from 2,000 feet above the mountain to 2,000 feet below it.
Mono Lake Paiute have long known about the unpredictable mountain winds. Lucy Parker shares a story that her ancestors have told about traveling through the passes to Yosemite to trade.
Going up Bloody Canyon, there's a story about the spirit that lives up there. When we walk through there, we have to be very quiet and respectful to this wind spirit, because if you're talking and not paying attention, a great wind will come up and it'll blow you off the trail.
Being respectful of the wind and weather is good advice. If you're headed into the mountains, tune into the local radio stations for the latest forecasts, because when it comes to preparing for the weather in the eastern Sierra, you don't want to walk around with your head in the clouds. Turn west off Highway 395 and drive up almost any eastern Sierra canyon. In 15 miles or less, you'll climb 4,000 feet to find sparkling lakes set at the foot of granite peaks that have been grooved, carved, and polished by one of nature's amazing geologic forces. If you're wondering how this stunning scenery came to be, you're in good company. When naturalist John Muir set eyes on Yosemite Valley and the High Sierra in 1868, he too was dazzled by its beauty and puzzled over its origins. Muir was fascinated by these frozen phenomena. Early surveyors had proclaimed there was nothing but traces left of these ancient glacial ice masses, yet Muir's travels in the Sierra Nevada high country led him to believe otherwise.
I was among the mountains, following the footprints of ancient glaciers that once flowed grandly from their ample fountains, reading what I could of their history, as written in moraines, canyons, lakes, and carved rocks.
As he rambled, Muir made painstaking observations of the region's geology, in particular, how glaciers shaped the landscape we so admire today. What was it in the landscape that he read? In his series of essays, Studies in the Sierra, the young naturalist explains how a glacier is formed.
Ocean water is lifted in vapor, crystallized into snow, and broadcast upon the mountains. Thaw and frost, combined with the pressure of its own weight, change it to ice, which, although in appearance is about as hard and inflexible as glass, immediately begins to flow.
In trying to express the amazement of it all, Muir's scientific writing becomes poetic.
By far the most striking of all the ice phenomena presented to the ordinary observer are the polished surfaces, the beauty and mechanical excellence of which no words will describe. They reflect the sunbeams like glass. Even horses and dogs gaze wonderingly at the strange brightness of the ground.
On a bright October day in 1871, Muir followed a mountain stream filled with glacial sediments flowing from a loose moraine of some 60 or 70 feet in height. His perseverance had paid off.
I saw what seemed to be a huge snowbank, 400 or 500 yards in length by half a mile in width. I shouted, "A living glacier!"
Muir's words weren't an excited exaggeration. Glacial streams and moraines are formed as gravity causes a glacier to move or flow as it spreads or slides. Glacial polish is produced because of the enormous pressure of the ice on granite rocks.
Glaciers do not only wear and grind rocks by slipping over them, as a tool wears the stone upon which it is whetted. They also crush and break, carrying away vast quantities of rock, not only in the form of mud and sand, but of splinters and blocks, from a few inches to 40 or 50 feet in diameter.
Decades later, the features that caught Muir's attention, U-shaped valleys, glacial striations, and rock-filled moraines, were equally intriguing for a teenager growing up in the Catskill Mountains of New York.
I can remember a textbook in high school that had a picture of a glacier very clearly, being drawn to it immediately.
Hassan Basajic turned that early interest into a master's project through his work as a researcher at Oregon's Portland State University.
Around 2001, when reports were coming out from other parks like Glacier National Park that glaciers there were retreating quickly, I began asking the question, well, what's going on with our little Sierra Nevada glaciers?
Relying on USGS topographic maps, which he had extracted into a digital database, Basajic documented evidence of 1,700 glacier-like features and 120 true glaciers.
Sierra Nevada glaciers are very specific, that they're all on the north sides of the mountains, which is what you'd expect because they're somewhat hiding from the sun. They're on moderate slopes and they're at elevations above 11,000 feet.
Narrowing the list down to a manageable size was the first step in the process.
I selected 14 of those glaciers and I used historical documents, things like aerial photographs from the 1940s and ground-based photos from early explorers of geologic features. So I reoccupied the spots where those early explorers took those photographs and created what were called repeat photographs. And what I found there was that over the 100 years, the 14 glaciers had shrunk by about 55%.
When International Glacier Authority Francois Mathis took part in a U.S. geological survey of the High Sierra in the early 1900s, he too discovered something quite surprising. Evidence that the Great Ice Age glaciers had melted away thousands of years ago. Those small living glaciers, charted by Muir and studied more recently by researchers like Basajic, were formed instead during a 700-year period of worldwide cold that began in the 13th century. To Mathis, they represented a new generation of glaciers. He called it the Little Ice Age. So, can travelers catch a glimpse of any of these Little Ice Age glaciers as they drive along Highway 395?
Yeah, there's a few that if you went up to them, you'd say, that's a glacier. One of them, which is the Palisade Glacier, that's located up from the town of Big Pine. There's cracks in it or crevasses, and there's large moraines, which are rock debris piles that the glacier creates. A lot of the other ones look like little patches of ice kind of smeared onto the sides of mountains.
The Sierra Nevada mountain range extends nearly 400 miles from north to south, making it well situated for glaciers, since it's nearly perpendicular to the Pacific Winter Storm Track. That location, combined with its great height, which averages almost 2 miles in elevation, contributes to the accumulation of packed snow drifting in on the howling gales of winter. What images come to mind when you think about glaciers? Is it towering slabs of crystal blue ice or immense snowfields where polar bears roam? Either way, there's probably something huge and dramatic about it. So why would someone choose to study the undersized glaciers of the Eastern Sierra? Pete Kirchner, an earth scientist at the University of California at Merced, explains his reasons.
For me personally, I think what's more interesting from a scientific perspective than just saying whether this is a glacier or that is a glacier is, where does this ice come from, what's it doing, and how does it contribute to the hydrology of the mountains? Some people have called the Sierra Nevada a large water tower. And in a sense, that's what they are, because they store water in them and release it slowly.
Glacier researcher Hassan Besajic reveals how this impacts life in the alpine environment.
The importance of the glaciers is that they act as kind of a buffer for streams and for wetland areas below. The flora and fauna are dependent upon that snow. So during really dry times, they could rely on these frozen reservoirs to buffer the existing amounts of water, so that if the glaciers go away, all of California is not going to be out of water. The main source of water is the snow. So it's more on a local level that the changes will happen.
That living glacier Muir discovered back in 1871 was just an icy patch on the mountainside when geologists revisited in 1949. And by 1977, it was gone.
For some people, the fact that there's glaciers in the Sierra at all is surprising. But I think what is important for people to know is that, hey, these glaciers are changing over the past 100 years, and they've actually shrunk by half. There's an organization, the World Glacier Inventory, that amasses all this information. And so that's where our information will eventually head. And that's where folks get ideas of how things are changing on a global scale.
So, as you make that side trip up in Eastern Sierra Canyon, consider yourself a student of nature, like conservationist John Muir, and take time to notice the footprints left by glaciers that began sculpting the Sierra Nevada almost 2 million years ago.
And when we trace their retiring footsteps back to their fountains among the high summits, we discover small residual glaciers in considerable numbers, lingering beneath cool shadows, silently completing the sculpture of the summit peaks.
Hopefully, like Muir, future generations will still be able to witness these powerful blue and white patches of glacial ice, reflecting sunbeams like glass.
In an alpine meadow high in the Sierra Nevada at 11,000 feet, under an astonishingly deep blue summer sky, a fat, yellow-bellied marmot lies basking on sun-warmed granite boulders. Energetic pikas, like farmers making haystacks, set plants and grasses out in the sun to dry and cure. Barely visible on a steep granite ridge, a small band of bighorn sheep pick their way across to tufts of vegetation growing on an exposed ledge, while a red-tailed hawk glides silently overhead, surveying the scene in search of prey. Many animals that make their home in the Sierra Nevada visit the alpine regions during the summer months. For them, it is a trip of opportunity. Grazing animals such as deer look for succulent shrubs. Predators like coyotes look to make a meal of the few small plant-eating rodents in the area, while mountain bluebirds chase after the insects that call the alpine zone their home year-round. When winter comes, these visitors move to lower, more hospitable elevations. The few animals that stay year-round have successfully adapted in ways that allow them to thrive and live in relative comfort in this cold, dry, windy, and snow-covered environment, even when there is no food or shelter to be seen. Wildlife biologist Rob Klinger simplifies their 3 survival strategies.
When you think about animals in these higher elevation areas, you instantly think, well, how do they make it through the winter? I mean, it's tough up there. So it's either eat like crazy, sleep like crazy, or get the heck out of there.
Living at elevations as high as 13,000 feet, yellow-bellied marmots are in the same family as squirrels and woodchucks. Wildlife biologist Thea Wong, who has been studying them since 2006, reveals that they prefer to sleep like crazy.
Their specialty is hibernating, and so that's how they deal with the shortened growing seasons and the extreme temperatures, snow and wind. And so they actually spend 8 months out of the year hibernating.
As a true hibernator, the marmot is able to decrease its heart rate from 95 beats per minute to just 3 beats per minute, and its body temperature hovers at just 1 to 3 degrees Fahrenheit above that of its deep burrow. Hopefully they've eaten well during the summer months, because marmots don't store any food. They just live off of all the fat they've put on during the rest of the year. By the time spring comes, they will have lost about half of their body weight. Often heard, but seldom seen in the high country, is the much-loved relative of the rabbit, the diminutive pika. Tom Stevenson, wildlife biologist for the California Department of Fish and Game, talks about these industrious, small-eared creatures that prefer to eat like crazy.
They actually go out and they collect vegetation during the summer and they dry it, and they actually make these little hay piles, and if you're in the Alpine you know what you're looking for. You can see these little hay piles. They have to collect enough food to get them through the winter, and then they bring those into a den, so they feed on those all winter long.
Although not often thought of as alpine residents, insects such as flies, beetles, and bumblebees also live at this elevation, pollinating the flowers and providing food for residents and visitors alike. As Yosemite National Park ranger, naturalist Karen Amstutz reveals, some of them do amazing things to stay alive here.
You know, there are something like 20,000 species of bees on Earth. Only 2 live in the alpine zone, and one of their ways of keeping from freezing is to shiver. This is something that we do when we're cold. Shivering actually warms our body temperature up. It increases our metabolism. So bumblebees shiver, and they can raise their body temperature 15 degrees by shivering.
Most of the permanent residents of the alpine zone are small rodents and insects. But the largest mammal to call this elevation home is the Sierra Nevada bighorn sheep. In 1999, when they were placed on the federal endangered species list, there were only about 100 bighorn left in the Sierra Nevada. A decade later, this population had grown to about 400. John Weyhausen, a wildlife biologist, has studied these magnificent sure-footed animals for 35 years and explains why these monarchs of the mountains have chosen to live in such high, steep places.
They're very visually oriented. Their eyesight is like us with binoculars. That's how they detect predators, and they need visually open habitats, which means very low stature vegetation. And in order to get that, they have to live under climatic extremes where plants essentially can't grow very high. And that means Arctic alpine systems and desert systems.
But despite their seemingly tough life, nature does provide. And many populations live in the alpine year-round.
Following most storms, you have a wind that comes and blows snow off of some of the slopes, and so you have these windswept high ridges that they can live on and pick little bits of forage to eat out of.
For the Sierra Nevada bighorn, whether they're looking for food or trying to evade predators, it's a way of life that often involves acrobatic maneuvers that any rock climber would admire.
One of the things that amazes you at times is their agility on steep rocky slopes. You watch an animal up there and you go, oh, don't slip, and then it stops and picks up its back leg and scratches its nose. And you realize this is nothing to them.
Depending on the availability of food, the bighorn will come down in the late winter and early spring to the base of the mountains to eat the newly sprouted greenery. Then join the other animals of the high country to live the good life in the short but fruitful days of summer. Yet in a matter of months, the whole scene changes. Winter winds roar over peaks and down through the canyons. The red-tailed hawk has flown to warmer, more hospitable climes. Bighorn sheep pick their way across the rocky heights in search of food. Tiny pikas bring in their harvest, while marmots, fat and glossy, waddle into their dens and close their eyes for a cozy 8-month sleep as the first snows of autumn blanket the meadows, transforming them into a cold, white world. But before that happens, ranger and naturalist Karen Amstutz tells us how we might get a glimpse of some of these resilient animals. But she warns, without a pair of binoculars, it won't be easy.
Because you're not going to be able to get really close to these animals. They're very shy by our perspective. They want to protect themselves from predators, and we're this big two-legged predator, and we're threatening to them. So if you can just be patient and sit out on a shady or sunny rock in the alpine zone, looking around for movement, you might see some amazing things.
Traveling along Highway 395 through the heart of the Eastern Sierra, our eyes are inevitably drawn to the granite mountaintops, 10, 12, even 14,000 feet in elevation. In this desolate realm of rocks, wind, and patches of snow, it looks as if nothing could survive. But a closer look reveals bands of trees climbing the steep rocky faces before giving away to the true alpine zone, where only the most dwarfed plants can be found. Botanist Dr. Elizabeth Wenck talks about why she studies the plants that grow in these incredibly harsh conditions.
My specialty is plant ecology, and I do that because I like understanding how plants work. There are just so many different conditions that plants have to deal with, and they can't run away like an animal can when it gets too hot or too cold or too dry.
To survive in this challenging environment, plants must find a way to adapt. Alpine winters bring many months of blowing snow and ice at temperatures below freezing. On bright summer days, baking heat and harsh ultraviolet radiation beat down through very thin air. Sparse sandy gravels offer little nutrition for the short 6 to 10 week season in which these plants grow. In these elevations, many plants adopt a pincushion growth strategy.
They're about 1 to 2 inches tall, and they have a single root, but then they just spread out into a big mound. The little ones really grow close to the ground because they're out of the wind and it's much warmer.
But for some plants, that strategy isn't an option. In the subalpine zone, at more than 11,000 feet in elevation, grows one of the most remarkable trees in all the world, the majestic bristlecone pine. These twisted sentinels have managed to live in places that no other tree dares to inhabit, and have lived thousands of years longer in the process. Lina Walker, former naturalist guide at the ancient Bristlecone Pine Visitor Center, describes the emotional impact felt upon meeting these ancient trees.
What the bristlecone teach me is living long is not in spite of a harsh environment, it's because of difficult conditions. I love to hike around them and draw pictures of them and paint them and just enjoy them.
Visitors to the bristlecone are delighted by the stark beauty, luminous golden colors, and twisted gnarled trunks set against the bluest of skies. Scientists are awed by their history.
What's really neat about the bristlecones is how slowly they grow, which means they've got really dense, tough wood, and therefore they can withstand the strong winds, they can withstand insect attacks, which is why they can grow for so many thousands of years.
Interestingly, the cold temperatures of this near-alpine environment play a big role in their development. As Dr. Elizabeth Wenck explains, there is a relationship between temperature and speed of growth.
At higher temperatures, you can grow faster, all biochemical reactions occur much more quickly, and so that's very beneficial to the plant.
In contrast, cold temperatures contribute to the slow growth that gives the bristlecone its enduring qualities. Arguably the oldest living trees, bristlecone pines have been studied intensely since 1953, when Edmund Shulman of the University of Arizona's Laboratory of Tree Ring Research identified the patriarch tree to be 1,500 years old. Subsequent studies found several trees that were 3,000 to 4,000 years old, with the oldest living tree in the area, Methuselah, almost 5,000 years old. A century in the life of this tree is like 2 years for a human. By comparison, the oldest giant sequoias are about 3,000 years old. The bristlecone's tenacity to maintain life is impressive. Their seeds often take root in dolomite, a limestone formation of alkaline soils where little else can thrive. In the harsh, high elevation where they live, the average annual precipitation is a mere 12 inches, so lateral roots help the trees absorb occasional rain and melting snow. Bending, sprawling, and twisting in persistent dry winds, These trees develop a dense resinous wood that protects them from invading insects and disease. But the ravages of time and weather take their toll, which is why bristlecone pines have adapted a unique characteristic known as strip barking. As the tree ages, its roots may become exposed by erosion and die. In response to this and other stresses, such as drought, much of the bark dies back, leaving only a narrow strip of living tissue. Pinus alpha, at more than 4,000 years old, measures 4 feet in diameter, but manages to survive with only a 10-inch wide strip of bark on its trunk. Christine Hallman is a dendrochronologist, which is a scientist who studies tree rings, the annual growth markers of a tree's life.
You have a chronology of your own life, right? For a tree, you have a chronology of rings or a time series of rings. So you have fat rings when things are good and you have narrow rings when they're bad. You can see precipitation over time and study temperature at the edge of the tree line.
Dendrochronologists compare ring patterns from many different trees under a microscope, lining up the identical patterns to create long timelines. These timelines provide climatic data that go very nearly back to 7000 BC, close to the end of the last ice age. Once tree ring climatic data has been identified, scientists can compare these dated conditions to known climatic conditions in other parts of the world, such as volcanic eruptions, droughts, and floods. The length and accuracy of bristlecone tree ring data has allowed scientists to recalibrate carbon-14 dating, a commonly used method of dating archaeological artifacts based on the predictable decay rate of the carbon-14 isotope. Despite all of the advanced scientific information the bristlecone provides, as Christine Hallman points out, the ancient tree still relies on a low-tech, some might even call it bird-brained way of continuing its legacy.
Nutcrackers use their seeds as food, but they also cache them and forget about them, and then the trees grow in certain patches someplace.
Naturalist Lina Walker reveals another fascinating fact.
Methuselah, the oldest known living bristlecone, is still making cones and still making seeds, which still make new bristlecones. Isn't that amazing?
In 1958, the United States Forest Service established the 28,000-acre ancient bristlecone pine forest in the White Mountains. If you'd like to visit this incredible natural resource, Bristlecone Pine Forest Visitor Center is usually open from mid-May through the end of October, weather permitting. Most roads into the Alpine Zone are open those same months. For more information, you can contact visitor centers throughout the Eastern Sierra.
Mono Lake appears as a deep blue oasis in a vast gray-green expanse of sagebrush desert ringed by high mountains and volcanoes. Sometime in the early 1860s, American author and humorist Mark Twain camped along its ancient shores and described his impressions of the lake in his book, Roughing It.
Mono Lake lies in a lifeless, treeless, hideous desert, 8,000 feet above the level of the sea. Now, this solemn, silent, sailless sea, this lonely tenant of the loneliest spot on earth, is little graced with the picturesque.
The lake and its surrounding watershed sit in a shallow basin formed by ancient volcanic peaks and mountain ranges. In his observations of what is thought to be one of the oldest lakes in North America, Twain wrote about a puzzling phenomenon.
Half a dozen little mountain brooks flow into Mono Lake, but not a stream of any kind flows out of it. It neither rises nor falls, apparently, and what it does with its surplus water is a dark and bloody mystery.
Happily, scientists have solved the mystery for him. Like the Great Salt Lake in Utah, Mono Lake is considered to be a desert terminal lake. As David Carl, a longtime ranger interpreter, reveals, that means water comes in, but doesn't go out.
There are 5 major creeks that flow into Mono Lake and provide most of the water that melts from the Sierra Nevada. There are no streams that flow out of it, but there is no outlet to the lake, so it's a terminal point. Terminal lakes, though, in the desert become salt lakes if they persist for a very long time. And Mono Lake is one of the oldest lakes in North America. It's at least 750,000 years old. That means that it's had a long time for the streams running into the lake, which are fresh, nice mountain water, but they're carrying minerals with them into the lake, and that accumulates.
Once water enters the lake, it can only leave by evaporation. Each year, almost 3 feet evaporates off the surface of Mono Lake. The dissolved salts and minerals left behind are what makes it 2 to 3 times as salty as the ocean and about 80 times as alkaline. Pure water has a very neutral pH of 7, but Mono Lake's water has a pH approaching 10, nearly that of baking soda or borax, giving it the feel of soapy dishwater. Mark Twain noticed the unique chemical makeup of the water in Mono Lake and used it to his advantage.
Its sluggish waters are so strong with alkali that if you only dip the most hopelessly soiled garment into them once or twice and wring it out, it'll be found as clean as if it had been through the ablest of washerwomen's hands.
When he wasn't doing laundry, Twain also spent time observing the inhabitants of this salty, alkaline inland sea.
Millions of wild ducks and seagulls swim about the surface, but no living thing exists under the surface, except a white, feathery sort of worm, 1/2 an inch long, which looks like a bit of white thread frayed out at the sides. If you dip up a gallon of water, you'll get about 15,000 of these.
What Twain saw were the Mono Lake brine shrimp, a species uniquely adapted to the lake's harsh conditions and a part of the ancient and extremely productive ecosystem here. The foundation of the lake's food chain is a population of single-celled algae that lives in the warm, shallow water. Trillions of brine shrimp consume this algae, and so do the alkali flies that form a thick black carpet along the shoreline. These harmless flies are often seen walking underwater, enclosed in tiny air bubbles. In their larval form, they provide a protein-rich food for the Quizzotica Paiute who call the Mono Basin home. As ranger interpreter Dave Marquardt points out, this abundance of shrimp and flies also provides a necessary and welcome stop for an astonishing number of migrating shore and water birds, such as the California gull and Wilson's phalarope.
As far as what makes Mono Lake important for these birds, it is essentially an avian gas station. And without the trillions of brine shrimp and the alkali flies here at Mono Lake, there would probably be little reason for many birds to stop here. But there's a virtual all-you-can-eat buffet for these birds on their migration routes.
But these avian wonders weren't the only things to attract Twain's attention.
Now, in speaking of the peculiarities of Mono Lake, I ought to have mentioned that at intervals all around its shores stand picturesque, turret-looking masses and clusters of a whitish, coarse-grained rock that resembles inferior mortar dried hard. How did they get there?
Weird and rather ghostly looking, these knobby spires are built by freshwater springs welling up through Mono's brine. Calcium in the fresh water combines with carbonates in the lake to form tufa, which is chemically identical to limestone. But not all desert terminal lakes are full of carbonates the way Mono Lake is, which is why these unusual towers may be a key in the investigation of still another life form at the lake, extremophiles. Laurie Newton, a limnologist or scientist who studies lakes, explains why an extreme environment like Mono Lake is a likely place to harbor some unique microbes.
High temperatures, little rain, high winds. The water gets very warm at the surface, cold at the bottom. So these are not your normal environments for organisms to survive in.
Recently, scientists of all the major disciplines have come together in a new field of science called astrobiology. NASA started this field hoping to further our understanding of how to look for life on other planets. Researchers like Dr. Jack Farmer at Arizona State University have been going to places like the hot springs of Yellowstone National Park, the glacial environments in the Antarctic, and the hypersaline waters of Mono Lake to look for the organisms that might live in these extreme environments.
By human standards, Mono Lake is an extreme environment. But if you're a microbe of the right kind, and in particular something called a halophile, literally a salt-loving organism, It's a wonderful place to live, and Mono Lake is, in many ways, best viewed as a microbial factory. And over the years has become a very interesting target to study to understand the potential for life in extreme environments, perhaps on other planets like Mars.
Mono Lake's tufa towers provide a classic place to look for these microbes. The rapid formation of tufa entombs microorganisms in the tower, leaving a microbial fossil record. Interestingly, meteorites from Mars have been found to contain carbonate globules similar to the Mono Lake tufa. Scientists hope to apply knowledge gained from analyzing the tufa microfossils to search for signs of extraterrestrial life. For Mark Twain, Mono Lake must have felt like visiting another planet. But in his many years as a ranger interpreter at Mono Lake, Dave Carl has seen firsthand how unbelievably vital and surprisingly full of life it is.
So this is absolutely not a dead lake. The good news is that now that it's protected and is recovering, it won't become the Dead Sea of California. We're not going to let that happen.
In his book, Travels with Charlie, American novelist John Steinbeck wrote, "The desert is a good school in which to observe the cleverness and the infinite variety of techniques of survival under pitiless opposition. The desert has mothered magic things." And what could be more magical than a delicate flower daring to bloom in a harsh desert environment? Characterized by extremely arid conditions, deserts receive less than 10 inches of precipitation annually. The Owens Valley and Eastern Sierra Slope are located at the juncture of the northern Mojave and Great Basin deserts. Summers here are long, hot, and dry, while winter temperatures can dip below freezing, bringing frigid winds and snow. Yet in this desert valley, icy creeks tumble past green ribbons of vegetation in a seemingly endless sea of sagebrush and scrub. Ironically, the towering peaks of the Sierra Nevada which spawn these streams make the Owens Valley a desert. The mountain's granite walls create a rain shadow effect, where moisture-filled clouds formed on the west side of this range are wrung dry by the time they reach the east side. Each desert has a different plant community, dictated by when it gets moisture and how much. The unique blending of these regions is the key to understanding the amazing diversity here. Botanist Steve McLaughlin, now retired from the University of Arizona, tells us this is a desert region unlike any other.
People ask me where I live, and I tell them, well, I live in a desert that has a trout stream. And they tell me, there's no such place. And I say, yes, there is. Well, this is the only desert I've ever been in, and I've been in most of the world's desert where there's so much water. All the rain falls in the winter.
The Owens Valley region is surprisingly rich in plant variety. Here you'll find hundreds of species and endless variations of carefully adapted organisms. But given such wide-ranging weather conditions, how do these plants survive?
When it gets really, really hot out there, animals can go hide under a rock or into the soil, but the plants have to sit there and take it. In the middle of the winter, when it gets really, really cold, they still have to sit there and take it. And that's not easy. I mean, if you try to understand how plants really function, what their chemistry is, what their metabolism is, all the physiology involved, those are complex problems.
Coping mechanisms of desert flora are among the wonders of the natural world. There are the drought endurers, perennials like creosote, that are well adapted to even the harshest of desert conditions. And some, as U.S. Forest Service botanist Sue Weiss explains, are drought escapers, annuals like the desert dandelion that go dormant when rains are scarce and provide a colorful display when conditions are favorable.
And those are plants that are called ephemeral, and they spend most of their life as a seed. They only are there when there's enough water. I had a teacher once who told me a seed is really a little plant in its own lunchbox. So the seed has plant food in it, and so when it gets the right conditions like water, then it starts to grow.
In the desert, perennial or year-round plants have nowhere to hide and must endure months of 100-degree temperatures and drought. Anna Halford, a botanist for the Bureau of Land Management, reveals their strategies.
Their main goal in a desert is to save water, so they've really had to evolve some pretty sneaky ways to not lose water.
Most have extensive root systems to capture scant rainfall and runoff. Some plant leaves grow vertically to minimize their exposure to the sun or to funnel water downward. Others have silver-gray coloring or waxy surfaces to reflect desert heat. Sue Weiss talks about a few more adaptations.
Sometimes they grow apart from each other so they don't have to share their water, and sometimes they actually poison each other.
Creosote bush is one of those unfriendly plants. The signature plant of the northern Mojave. It covers millions of acres in the southwest. You may have seen the yellow pinwheel-shaped flowers that appear on its rangy branches after a generous rainfall. But the rest of the time, this evergreen shrub is covered with tiny green leaves that are waxy and resinous. Botanist Anna Halford thinks of the creosote bush as the ultimate desert survivor.
This resin is amazing because it protects the plant from disease, it protects it from predators that like to chew on the leaves, and that chemical actually gets into the roots and it repels other plants from living too close by. So it keeps its environment in such a way that it can obtain water and nutrients without competing with another plant, essentially. So you'll see, if you go out, you'll get to a high point like a ridge and you'll look down and you'll go, God, it looks like somebody planted these creosote, because they're just perfectly evenly spaced with about 5 to 6 feet in between each one of them, which is the limit of that chemical barrier.
The Great Basin Desert begins in the upper Owens Valley. Here, gray-green sagebrush reigns supreme. Sagebrush ecosystems have the largest habitat range in the United States, covering nearly 470,000 square miles across 11 western states. While its common name brings to mind the herb that seasons our Thanksgiving dinner, this desert plant isn't related to salvia, the true sage, but is actually part of the sunflower family. Sagebrush grows where little else will, making it important for wildlife. This perennial shrub provides a home for birds, insects, and other animals, such as pygmy rabbits and sage grouse. However, the plant's volatile oils, which contribute to its pungent turpentine-like fragrance, make sagebrush hard for most animals to digest. So its silvery leaves remain largely uneaten until winter, when they become the last resort for hungry mule deer, domestic livestock, and other small mammals. Rick Carbon, professor of entomology at University of California, Davis, has studied sagebrush for more than a decade and has discovered that its scent is more than a powerful perfume. In fact, his current research finds that these plants are up to much more than we ever suspected.
Amazingly enough, I think that this sagebrush system is really one of the models for plant communication. We have found that sagebrush uses a volatile system involving gases and cues that are contained in those gases to communicate information from one part of the plant to another part. Herbivores, by and large, don't like the smell of sagebrush, but from my point of view, it's a fantastic smell, and it's a real part of this Great Basin Desert. When sagebrush is attacked by these herbivores, it changes in ways sort of like our immune response that make the sagebrush plant then more resistant to subsequent attacks. The fact that plants are able to respond to things that happen to them is very similar to the kinds of behaviors that we have in the past thought only animals, maybe even only humans that have central nervous systems, are capable of these kinds of sophisticated responses.
Carbon is excited by the implications of these findings and sees the promise of these volatile organic compounds.
So that instead of, for instance, spraying pesticides to protect agricultural plants, if we can manipulate the plant's own defenses in this way, it might provide a much more ecologically rational way of managing pests.
All the plants of the Eastern Sierra share a common trait: the ability to survive in a land of extremes. As Richard Stewart, an artist and teacher from the Big Pine Paiute tribe, points out, Native Americans have thrived in this desert land by keenly observing these plant communities.
There's medicinal plants here. There are plants that were used for fuel, for fires.
You had people who specialized in what plants made the best bows, what plants were the best to eat when they grew. So everybody really had a bit of knowledge about plant life.
In this land of little rain, you'll find bushes and trees that live for thousands of years, and wildflower seeds that can remain viable for decades, waiting for the right moment to germinate. This is your invitation to look, listen, and feel this desert, and discover its magic for yourself.
Desert. The very word implies emptiness, a lifeless void, and traveling through the desert at midday seems to justify that conclusion. On the other hand, the blur of sun-baked sagebrush shimmering in the desert heat and the occasional small animal darting across the road reminds us that there is life in this desert, a rather secret and mysterious life. Lying like an enormous trough between two high mountain ranges with the Sierra Nevada to the west and the White Inyo to the east, the Owens Valley gets less than 10 inches of rain a year, qualifying it as a desert. This region also lies at the juncture of the hot, dry Mojave Desert and the Great Basin Desert, characterized as colder and wetter due to its winter snows. Animals in this desert must adapt to the challenges of heat and drought, wind and cold. Each one has developed amazing mechanisms to make this extreme environment their home. It's helpful to think of desert animals as falling into two groups: endurers, animals that have physiological or behavioral adaptations to tolerate the heat, and evaders, animals that have adapted to scorching temperatures by avoiding the heat altogether. A good example of an evader is the kangaroo rat.
I really enjoy talking about the kangaroo rat because they have so many different adaptations to the desert that it makes them a really fascinating creature.
Bureau of Land Management wildlife biologist Joy Fatu describes these desert dwellers.
There's something irresistible about a kangaroo rat because it has this big head, it has big eyes, it has fairly big ears, at least not tiny ones like some rodents have.
While these features might make them greeting card cute, they are actually important adaptations to their nocturnal life. Acute hearing and vision help them to avoid nighttime predators like owls and snakes. But there is also another benefit to the kangaroo rat's after-hours lifestyle.
What's helpful about being nocturnal is that they avoid those hot temperatures of the desert during the daytime, right? They dig really deep burrow systems, up to about 3 feet deep, that they stay in during the day, and they have all of their necessary little components, their nesting areas and their eating areas and food storage areas, in that system of tunnels way down under the ground.
Kangaroo rats can survive without ever drinking any water, as they get all the moisture they need from their diet of seeds, which they carry to their burrow in a very special and surprising way.
It really can't afford to lose that moisture when it's running around carrying seeds in its mouth. And so it keeps them instead in dry, fur-lined pouches on the outside of its face.
Joy offers a suggestion on how to catch a glimpse of these cute, long-tailed rodents.
Your best opportunity to see them is when you're out at night, if you're driving and you're watching your headlights and you see something go boing, 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 boing across the road. It's very likely a kangaroo rat. Slow down, see if you get a look at its big hind legs and its big tail that it can actually use for steering itself in mid-hop. You know, for its size, it's pretty impressive that it can hop 10 feet or so in one bound.
An example of an endurer is one you are very likely to come across during your desert travels, the black-tailed jackrabbit. So what helps this member of the hare family to endure the heat? Joy Fatu reveals their secret.
What's one of the really distinctive physical characteristics of jackrabbits? Big ears. Did you know that those ears are radiators? Just like a car has its fluid circulating through a radiator where a lot of airflow can go through there and cool it off, right? Exactly the same thing is happening with the jackrabbit's ears because its blood circulates through those big, tall, thin ears and is spread out over that big surface, and that cools the whole animal.
Blacktails have always been plentiful in this desert. Don Bakich, a member of the Big Pine Paiute Shoshone tribe, tells how this animal provided numerous resources for the valley's native people.
I was thinking about it this morning, and the rabbit was like the Owens Valley buffalo. Of course, they ate them, and they made blankets out of the skins, and the small bones, they could, sharpen them down and make needles out of them, so the rabbit was real important.
You might be surprised to hear that fish were once as common in the desert as the jackrabbit. Thousands of years ago, when the great Ice Age glaciers melted, interconnected lakes and rivers covered much of this desert region. As these glacial waters receded, the Owens pupfish, a tiny silvery 2-inch fish, became stranded in isolated springs and pools. At one point, they were thought to be extinct. Phil Peaster, an aquatic biologist now retired from the State Department of Fish and Game, was one of the scientists who rediscovered these little fish out at Fish Slough, a marshy oasis about 10 miles north of Bishop. He tells the story of how they survived.
I had a grad student. He came into the office and he said, "Phil, that pond's drying up. We're going to lose the pupfish." And I then went out to take a look at the fish, and the fish in the stream were in bad trouble. So I had 2 buckets with me with these battery-powered aerators. I put all of the fish left in the buckets with the aerators going full blast to try to get enough oxygen to keep them alive. I took off with the buckets, and by then it was pretty dark. All I could think was, hoping to heck I didn't fall, because if I'd fallen, the fish would be extinct.
Department of Fish and Game aquatic ecologist Steve Parmenter explains the major recovery program that grew out of the rescue of this entire species.
So it also underscored the need to actually transplant these fish around and have replicate populations so that all of our eggs were no longer contained in one basket, all of our fish in one pool. So that's been done since 1969 to the present.
Pupfish can live in pure water or water many times saltier than the ocean. They can survive in very shallow water and at times even mud. And while pupfish can live in freezing water, they are the only fish that can also survive in water warmer than 100 degrees Fahrenheit. Their remarkable physiology certainly qualifies them as endurers.
They have kidney function that we could only hope to understand. So there may be biomedical lessons to be learned from this species. The reason why I think we should conserve them is ethical. We share the planet with them. Through our carelessness or worse, we could make them extinct, and I just don't think that we have the right to do that.
You may have to go off the beaten path to see these tiny fish, but in your travels through the Owens Valley, keep an eye out for other desert dwellers like coyotes, skunks, lizards, and maybe even a red-tailed hawk. Austere, sparse, and seemingly barren at first glance, Joy Fatu reminds us just how special this desert is.
The desert animal community that we have in the Eastern Sierra is pretty much intact. And that's something that you don't find throughout California, certainly not throughout the United States. There are places where the native animal community has been altered almost to where it's unrecognizable from what it used to be. Here we have pretty much the animals that we've always had. And although there aren't a lot of them, it's wonderful to know that they are the animals that belong in this ecosystem and that this ecosystem is intact.
As you journey through the Eastern Sierra, we hope you've enjoyed this audio traveling companion and that you discover the rich cultural and natural heritage of this stunning landscape, as well as the contributions science has made to deepen our understanding of the region. Funded by a generous grant from the National Science Foundation, these programs are an introduction to the wonders of this land. And now, looking out your window with new eyes, we hope you find yourself wanting to know more. We invite you to stop in at local visitor centers and museums along the way and explore our website at www.roadsideheritage.org to expand your experience. Welcome to Roadside Heritage of the Eastern Sierra, a series of audio programs celebrating the region's natural and human history as seen through the eyes of science. The Sierra Nevada mountains run like a 400-mile backbone along the eastern edge of California. In its shadow lies the Eastern Sierra, a land where snow-capped peaks plunge to meet high desert basins and ranges, where the drama of Earth's dynamic geological forces have created a landscape both harsh and beautiful. So how did this landscape come to be? And how has life been able to adapt to such an extreme environment? In this program, we'll explore the story of the mountains themselves and experience some of the destruction, upheaval, and regeneration that took place to create them. Steeply and dramatically, the Sierra Nevada rises before you. Did you know that this mountain range runs half the length of California, and that much of its body is made up of granite? Those immense saw-toothed peaks of gray-speckled stone, some reaching as high as 14,000 feet, certainly command your attention. But as you travel along scenic Highway 395, you might be surprised to find out that the mountain range you're passing is not the first, but the second rising of the Sierra. There's some truth behind the folk saying, older than the hills. Still, to understand how the ancient granite that makes up the present-day Sierra came to be, we have to ask a few questions. What exactly are mountains, and how are they formed? As geologist and chemist Don DiPaolo, a professor at UC Berkeley, points out, mountains don't just appear out of thin air.
The Earth has this peculiar characteristic that most of its surface is either just above sea level or about 5 kilometers below. And in fact, no other planet in the solar system has this bimodal or two-level crust on its surface. So to make mountains, you have to do something to the crust.
That something involves the principle of plate tectonics. Millions of years ago, incredible forces within the Earth tore the outer crust into rigid plates. Some of these plates carry whole continents. Others carry ocean floors with seas on top. Some carry both. The plates drift slowly in different directions, like giant rafts atop the semi-molten portions of the mantle that encircles Earth's superheated core. In some cases, when two plates carrying continents collide, the gradual pressure causes the crust to become folded in great corrugated waves, which is how Mount Everest and the surrounding mountains of the Himalayas were formed.
Tibet is a very simple and clear example of two continents that have collided and caused a very large mountain range and plateau to form. It's a little bit trickier to tell the story of the Sierra Nevada.
That's because mountain building takes place in several different ways. The granite of the ancient Sierra developed more than 160 million years ago, around the time dinosaurs roamed the Earth, when two tectonic plates encountered each other along the southwestern edge of what would become the continent of North America. One was a thin oceanic plate, about 3 to 6 miles deep, made up of basalt, a dense rock rich in iron and magnesium. The other was a thick continental plate, anywhere from 12 to 50 miles deep, composed of a mixture of different rocks, many containing lightweight minerals such as silica, which made the plate buoyant like an ancient ice cube. But when the two finally met in a head-on collision, they didn't just buckle into giant folds. In addition, the dense oceanic plate pushed itself under the lighter land plate, much like the way a powerful NFL running back would dive underneath a defensive tackle while driving for the end zone. Of course, the actual event, a geologic process called subduction, took place so slowly that you would have had to wait 100 million years or so for the instant replay. But what you would have seen is how the oceanic plate was forced down, broken apart, and completely consumed, while dragging along with it sediments, seawater, and large chunks of the continental plate. There, miles below the Earth's surface, temperatures of up to 2,000 degrees Fahrenheit melted and mixed the debris together, causing some of this hot fluid rock or magma to rise back up toward the surface, where it pushed through breaks in the crust and erupted as a chain of volcanoes. Think about the heated wax inside of a lava lamp, and you'll get the idea. Although this first rising of the Sierra created a mountain range as tall or taller than the one you see today, geologists believe that the ancient Sierra also contains several volcanoes similar to the ones found in the Cascade Range, like Mount St. Helens, Mount Rainier, and Mount Hood. Yet most of that magma didn't even make it to the surface. The melted rock stayed underground, cooling down to form enormous masses and slabs of granite-like rock called plutons, named for Pluto, the Greek god of the underworld. But since this rock was so hot, the cooling took quite a long time. That gave the various minerals a chance to crystallize and grow, which is one of the reasons granitic rocks have a salt and pepper look to them. Hold one of these rocks in your hand, and you can actually see for yourself the white crystals of quartz and feldspar, along with the dark crystals rich in iron and magnesium that were heated and cooled eons ago in this geologic melting pot. Imagine being able to touch something very ancient that was created in Earth's most fiery furnace millions of years ago. But if there's one thing a geologist knows, it's that the passage of time can have a huge impact on the Earth's surface. And so, for the next 50 million years, wind, water, and ice eroded the volcanic rock of the ancestral Sierra Mountains down to relatively low-lying hills around 3,000 feet high. The debris caused by all this erosion was carried away and deposited as sediment. To get an idea of the sense of scale, consider that below some parts of the Owens Valley floor and Highway 395 are layers of this sediment that are 4 to 5 miles deep. This erosion also exposed the massive plutons of granitic rock that were buried below the first mountain range. Called a batholith, this is the rock that forms many of the saw-toothed peaks of the present-day Sierra. But if the Sierra Nevada were whittled down to mere 3,000-foot hills, how were they transformed into towering mountains once more? One of the longest ongoing debates between Earth scientists is about exactly when and how this mountain range was uplifted a second time. Berkeley professor Don DePaulo admits the answer is far from a slam dunk.
One would think the mountain range that's as prominent as the Sierra Nevada that we would know all about how it formed. But in fact, it's an area of active research now, and we're still not sure we understand why this huge mountain range is there.
There is agreement, however, that when it comes to the Earth, geologic change is bound to occur. About 25 to 30 million years ago, the North American continental plate came into contact with another oceanic plate. During this period, a substantial amount of thinning and stretching took place in an area called the Great Basin, a vast region that spans from the eastern edge of the Sierra to about where Salt Lake City, Utah stands today. Geophysicist Dr. Stephen Park helps put it into perspective.
In other words, if you were to think about taking a plane from Denver to San Francisco 30 million years ago, it would take half as long as it takes now. That whole area has stretched. When you stretch like that, the crust gets thin and also breaks up.
While this stretching is still going on, evidence of that breakup can be seen in the formation of ranges like the Inyo White Mountains visible to the east, and the creation of enormous basins such as Owens and Death Valley. But there were other forces that came into play to cause the second rising of the Sierra, an episode of mountain building that took place in the blink of an eye when compared to similar events on the planet's geologic timeline.
Increasingly, the evidence is showing that 8 million years ago, the Sierra Nevada started coming up, and in the range of 2 to 4 million years ago, experienced an accelerated uplift.
As a result, the ancient Sierra Hills were turned into the spectacular mountain range we see today. Specifically how that happened is a source of intense scientific debate, but it's generally accepted that at least two forces were likely involved. Not surprisingly, one of them involves plate tectonics.
You've got three major ways in which plates can interact. They can come together, they can pull apart, or they can slide past one another. And California has examples of all three of those kinds of plate margins in one state, and they're active now.
Pinch anything, whether it's the skin on someone's arm or the dough for the crust of an apple pie. When you apply pressure from opposite directions, it's going to cause whatever is in between to rise. This pinching motion between the oceanic and continental plates is responsible for some of the second uplift of the Sierra Nevada. Other components that could be involved in the rising are the upward buoyant force of the lighter weight granite on top of the denser iron-rich basalt, or an underground molten pluton of rock could be pushing the mountain range up from below. And as geophysicist Dr. Stephen Park points out, it is often the knowledge of a few things in particular that leads scientists to ask even bigger questions about something else.
So the question basically is, if we think we understand all the buoyant forces creating the Sierra Nevada and the forces that are there to produce the uplift, why did everything hang around doing nothing pretty much until the last, say, 8 to 10 million years? And then suddenly lots of things take place. That's the basic question we're trying to understand here. That's what's so exciting about it, is to try to understand it.
Until that answer is discovered, scientists, as well as artists, poets, and men and women from all walks of life will continue to contemplate and appreciate the spectacular mountain range and everything it has to offer. Ansel Adams, one of the 20th century's most acclaimed photographers, focused his camera lens time and again on the majestic face of the Sierra Nevada. He explained the reason this way: no matter how sophisticated you may be, a large granite mountain cannot be denied. It speaks in silence to the very core of your being. As you travel the 220-mile Eastern Sierra Scenic Byways with its scenic pullouts and kiosks, we invite you to get off the highway and stop at one of the visitor centers, museums, or chambers of commerce. You'll find that local residents are more than willing to share their passion for the region. By exploring on your own, you will truly come to appreciate all this diverse and dynamic landscape has to offer.